Today, my name is Sameer Shinde, and I serve as the Research Associate Professor and the Director of the Performance Research Lab at the University of Oregon. I also serve as the President and Director of Paratools Inc. And today, I want to talk about how we can use the Spack package manager to install software that we use in our E4S project, targeting CPUs as well as GPUs. I'm working as part of this team from the Department of Energy's Exascale Computing Project. And one of the problems we are trying to address is that as our software gets more complex, it's getting harder and harder to now install our tools and libraries correctly in an integrated and interoperable software stack. So we have a project called the Extreme Scale Scientific Software Stack, or E4S, which is a curated Spack-based distribution of tools and libraries for HPC and AI and ML. And it includes vendor software stacks as well. It includes Intel One API. It includes NVIDIA's NVHPC, AMD's ROCm, and it features binary build caches as well as containers for HPC. You can learn more about it at this e4s.io webpage. But before I delve into that, let me just give a brief introduction to the Exascale Computing Project, or ECP. In ECP, we have three different areas: the application development, software technology, and hardware and integration. And our goal is to create scientific applications that scale well, deploy the tools to the DOE HPC facilities, and create an integrated software stack. There are many R&D projects that are of interest to the general HPC and AI/ML communities, and I'll take some time to describe what kind of tools we have in the software technology focus area. We have over 71 unique software products, and this spans a broad range of tools and numerical libraries, including programming models and runtimes, math libraries, data and visualization. This is our roadmap to exascale systems. We'll soon have exascale computing systems in the US, and starting from this 2012 to 2020 time, we had systems at Oak Ridge National Labs, Argonne, Lawrence Livermore National Labs, and Lawrence Berkeley National Labs. And these include the IBM Blue Gene systems, the Mira system, our current top system, the Summit at Oak Ridge National Labs, which is an IBM Power 9 system with 6 V100 NVIDIA GPUs on each node. And we have another system at Lawrence Livermore National Labs called Sierra. Now, going into the 2021 to 23 timeframe, we have already deployed the Perlmutter system at Lawrence Berkeley National Laboratory in Berkeley, California. And at NERSC, this system has A100 GPUs from NVIDIA, and it's an HPE Cray system. We also have other systems like the Frontier system, which will be an HPE AMD system with AMD GPUs at Oak Ridge, and Argonne National Labs will host the Intel HPE system. Los Alamos Sandia will host the Crossroads HPE Intel system, and Livermore will host the HPE AMD El Capitan system. And these are the exascale systems. So our extreme scale scientific software stack is focusing on the ECP software technology area. Our goal is to build a comprehensive, coherent software stack that enables application developers to be highly productive and to develop parallel applications that target diverse range of exascale architectures. And as I mentioned, we have GPUs from Intel, we have GPUs from NVIDIA, as well as AMD. So our software stack should be geared towards scalability with massive on-node parallelism. We want to extend the existing capabilities when possible and develop new ones when not possible. And we want to guide and complement and integrate with the vendor efforts. That's why I mentioned the software stacks from the 3 different vendors. We want to deliver and develop high quality and robust software products. And we have 6 technical areas. There's a 7th area for workflows. And these areas span programming models and runtimes, development tools, math libraries, data and visualization, the NNSA software technology projects, and the ecosystem, the software ecosystem project that's developing the E4S distribution. We work on products that application developers need now and also look into the future. So you may have already used some of the products, including MPitch and OpenMPI MPI distributions. We are working with compilers, including LLVM, and creating new capabilities in LLVM. We have support for performance portable libraries such as Raja, Cocos. We have OpenMP, OpenACC libraries integrated in LLVM compilers. We have performance evaluation tools, including PAPI, Tau, HPC Toolkit, math libraries such as BLAS, sparse solvers, Trilinos, PETSI, HDF5, MPI IO, Adios 2. These are all IO libraries. We have data and visualization projects, including Visit and ParaView, and a large number of these projects. So the software technology teams are creating new algorithms that effectively expose and exploit the massive on-node parallelism within the node. These include the use of GPUs. These include the use of accelerators from a number of different vendors. And even OpenMP and OpenACC programming models are used to target on-node parallelism, while MPI is used for cross-node. And these ST products are expanding support to all 3 GPU architectures from NVIDIA, AMD, and Intel. And the teams are increasingly relying on these software technology products to get performance and portability in their applications. So with this, our goal in the E4S project is to have software that is of better quality, has the documentation. It's a curated release, so we have integration, testing, we deliver this to the facilities, and we make it easy to deploy these packages. There's a strong commitment to quality. We have a doc portal that is a single portal for all the products that are included. There is a portfolio testing. We have curated collection in such a way that we don't, we make it simple to deploy the packages. And we have quarterly releases. We just had a 22.02 release. We have build caches, which can speed up your installation of packages by 10x or more, a turnkey stack, and even a strategy group that comprises agencies, industry, and international partners. But why do we need all this? Why do we need the E4S project? And the answer is that scientific software is becoming extremely complex. And you can see this in the dependency graphs. Here is the graph for NALU, which is a generalized, unstructured, massively parallel, low Mach flow solver from Sandia National Labs. And you can see that NALU depends on a package called Trilinos. Trilinos depends on Boost, Parmetis, Sweet Sparse, which depends on Metis. It depends on Netlib, Scalapack, SuperLU, OpenBLAS, OpenMPI, and you can get the idea. There's a large number of dependencies, and all of these packages must work together for the solver to function. And here is the dependency graph for Deal2, which is a C++ finite element library. And you can see the complexity growing in our software packages. This is the dependency graph of R miner, the R data mining library. And you can see how it depends on so many different packages which have to be correctly installed and functioning on the target architectures. And even proprietary codes, for that matter, are based on many open source libraries now. Here is the dependency graph of Aries, and half of this directed acyclic graph is external, and more than half of it is open source, which is shown in all blue boxes here. And nearly all of it needs to be built specifically at the HPC centers to get the best performance. So we are building an entire ecosystem in the Exascale Computing Project. We have over 15 applications with over 80 software packages, which target different architectures and platforms, including Intel Xeon, AMD, EPYC, Power 9, KNL, NVIDIA, ARM, all the way from laptops to supercomputers, which includes a number of different compilers. It depends on different programming models and many versions of each of these packages, which can lead to a combinatorial explosion. And every application has its own stack of dependencies. It has become so complex that now many facilities are dedicating several FTEs to just building and porting of these applications. They often trade the reuse and usability for performance. And we must make it easier to somehow rely on other people's software. But how do we install software? How do we install software on a supercomputer? When you have so many dependencies, you first start with downloading all of these 16 tarballs that your application may need, and you start building them. And you start building them one at a time, like this, where you use the configure command for each package, you do the make, you fight with the compiler flags, you type make, you tweak the configuration arguments, you configure, you do the make install, and then you use CMake for some packages, you use autoconf for others, and then finally you get them to build together and you run the code. And then it can segfault and you can start all over again. But then you may say, what about modules? Well, many supercomputing environments form some form of environment modules. And this dates back all the way to 1995. And there's work in the Tickle modules and the LMod from TAC, which are very popular. So you can just say module load GCC and it will load the compiler. But it does not install the package. Modules just set your environment. They alter your LD library path, your path environment variables, but someone else, likely a team, has already installed these packages like GCC for you. And you can only say module load or unload to access that. So the Spack package manager is a key contribution for E4S, and E4S uses this package manager for software delivery. In fact, now all the DOE products in ECP have standardized on using the Spack package manager, which comes from Lawrence Livermore National Labs, to provide the software delivery for ECP. Spack provides the ability to specify different versions of software packages. It can allow you to specify compilers. It can allow you to specify MPI and other variants for GPUs. And it's a build layer. It's a big project. It's not only for E4S, but also a large collection of software tools and libraries outside of ECP Software Technology. And you can learn more about Spack by going to this spack.io webpage. And it's very easy to install this flexible package manager. It supports both CPUs and GPUs. All you have to do is do a git clone on the Spack repo, source an environment file, and then you are ready to install a package. You can say Spack install tau, and then it will install tau and its dependencies within the Spack directory. But unlike many typical package managers, Spack can also install many variants of the same build of the same package, which is configured and installed in different ways. And I mean, you may want to use different compilers. You may want to use different MPI implementations, the message passing interface library, which allows you to communicate between multiple nodes. You can build different options as well. You can learn more about Spack here, and there's a GitHub site. Spack allows you to set up not just the environment, but also the compilers. You can say Spack compiler find after sourcing the environment file, and then Spack will find the compilers and list them. These could be compilers like GCC, Intel, NVIDIA, HPC. You can also say Spack external find. And this is interesting command because you can then pick up other packages that are already installed on your system. You may have M4, AutoConf, tar, a number of different tools that you don't want Spack to build from the source code for a given compiler. You just want to use it, and you can provide that. You can edit files in your .spack directory. There's a packages.yaml file. There is a modules.yaml file where you can specify how to set up modules. And then you can just use that to install packages. You could say Spack install tau. But it also understands versions. And you could say, please install version 2.31 by using the @ symbol after the name of the spec. So now you can say, please install tau version 2.31. You could also say, but I want to use GCC version 930 while installing tau. And there is a percentage symbol which allows you to specify a compiler. And these are the same compilers that we have already found in the Spack compiler find command. Okay, so now I can specify compilers. I can also specify build options. I could use variants that are there in that recipe and say Spack install tau version 2.31 using the GCC compiler, which is got a version of 930, but enable some options. Now, if I'm using an Intel GPU, I may have a board like a DG1 discrete graphics GPU, and I can say plus level 0 or plus OpenCL, and then it will enable the OpenCL and level 0 options. You can say Spack install tau with MPI, where MPI is provided by the MVAPH2 tool, which has a version of 2.3, which is built without the wrapper RPath variant, so that there's no RPath while building the MVAPH2. You can substitute this MPI with a system MPI, and then you can build a specific version of the tool just the way you want it. Spack is expressive enough with its syntax that allows you to do this. It can also connect with a build cache, where you have a mirror of binary packages that are already built for your project. So you don't have to compile everything from source code again and again. When you say Spack find, it will show you the different packages. Now, this is on an IBM Power 9 system. You can see Ubuntu 1804, PPC64LE, Power 9 LE, and you can see Trilinos version 13.0.0 is built over here. You have SuperLU version 6.3.0 or 6.3.1. And then you can say Spack load SuperLU dist at 630. And multiple versions of the same package can coexist. And you can automatically install and load the correct version of the package. And binaries work regardless of your user's environment. You can also export these packages in module files. So Spack also generates module files which you can use. And it is essentially central to our ECP software strategy. This allows us to enable software reuse for developers, users. The roadmap is packed with new features, and you can learn more about it at the spack.io webpage. I want to show you how we are using this in these applications. So we have applications. There are 5 applications that I'm just picking up. There is one called ExaWind, which is a turbine wind plant efficiency CFD solver package. And it comprises of AMR wind, adaptive mesh refinement wind package, and the NALU wind package. NALU, the same solver that I showed earlier. It has a lead institution of the National Renewable Energy Laboratory in Golden, Colorado. And we are collaborating with this team. There are other packages like Subsurface, WDM app, or the whole device modeling app for preparing for ITER experiments. This is a fusion code for the confined fusion plasmas. And the lead is C.S. Chang from Princeton Plasma Physics Laboratory at the Princeton University. Is Exascale, which includes the cosmological simulation with lead from Argonne National Labs, the Marble Multiphysics code from Lawrence Livermore National Labs. And you can see that all of these codes, which are shown in different shapes over here, have a need for different packages. These are many of these software products that all of them use. And you can see across different areas which one of these codes are using which packages, like this. So you can see that we do need a way to create a distribution, a software technology, software stack that spans multiple areas. These are software development kits. I lead the SDK effort in the programming models and runtime area over here, which is responsible for building the E4S distribution. But we have compilers in support, software development kits, tools and technology, which includes Tau. The Tau performance system is another tool that our team at the University of Oregon has developed along with the program database toolkit. The XSDK package, the Math SDK, which includes solvers like SuperLU, Trilinos. We have visualization, analysis, and reduction tools like ParaView, Catalyst, VTKM, Visit. You may have heard of ParaView and Visit tools already. There's scalable checkpoint restart. There are other data management libraries like HDF5, Adios2 that are part of the data management IO services checkpoint restart SDK. We have the ecosystem and E4S at large. And there are all these different SDKs, and we build the package, we test it, we deploy it. This is the whole cycle of developing the package and installing it for different SDKs, including math, libraries, data and viz, programming models, and then it integrates and builds the whole E4S distribution based on these SDKs. So the E4S is a curated Spack-based software distribution. And we support 3 different architectures: x86-64, the IBM Power 9 PPC64LE, the ARch64, ARM64, and we have container images. These are available on Docker Hub. They are available on the E4S web page of pre-built binaries of all of these products. We have base images as well as full-featured containers, and these have support for GPU runtimes. You can pick a full-featured release which has all these different products, or you can pick a base image, just plain Ubuntu image for your custom images, or you can pick an image which has GPU support from one of the 3 vendors. We also have recipes on how you can create these custom images from the base images. We have support for integration in GitLab, even a validation test suite. I mean, it doesn't matter how we install the package, it must do what it is supposed to do. And there are test cases that are integrated in our validation test suite that will help you compile, build, run the code, and make sure that the package is doing what it says it should do. If you are just getting into this area of container runtimes and you want to explore, we also have images from Docker, Singularity, Shifter, Charlie Cloud, all integrated in the E4S VirtualBox image. You can use this for learning more about this. We also have an AWS and GCP image to deploy E4S. So the questions that we are addressing are, how can new ECP software capabilities be effectively and efficiently integrated and sustained? we are looking at how E4S can build upon, leverage, and extend the existing capabilities and activities using Spack. How can E4S become a sustainable, open, and collaborative software ecosystem for HPC and AI/ML? And this is something that we are working together with the Department of Energy and other US agencies, industry partners, and even international institutions to deliver the value proposition of the ecosystem of this software stack. And we want to build an open hierarchical software ecosystem based on Spack. And we start with the software technology products. We integrate with SDKs and create the E4S. So you can see how a new project can join the E4S project. We have community policies over here. And these policies lay out what is needed for a product to join the E4S. The membership criteria for E4S has 9 different policies. And these are simple policies, common sense policies that the community has helped develop. The first important policy is that it must have a Spack package so that we can install it. It should have a validation test suite integrated in the E4S test suite. You can issue a pull request and get a new test case so that we can check that the package builds correctly. There is a post-installation test, and there's some quality control. We also have a doc portal which has documentation, access to change logs, README files, license files. So the product information can easily be accessed from a single point in the E4S portal. Now, starting from our release in October 2018, where our first release had like 24 packages, we just had a release last month where E4S 22.02 had 100 different release products. I lead this effort as the technical lead, but it has containers, it has from source builds, it has cloud images, it has binary caches. This is the main effort from the Exascale Computing Project, and it includes the HPC tools, but it also includes AI tools. This is interesting because these tools are often very hard to install correctly and target the GPU that you're interested in. You may have tools like PyTorch, TensorFlow, which use CUDA, ROCm. There are co-design packages like Amrex, Kibana, MFEM. All of these are included in E4S. There are notes over here on how to install this on bare metal platforms. So if you are starting with a new cluster, you could just download a single Spack file and then build the entire ecosystem of tools that you want by just cherry picking the packages that you want or don't want in the recipe. Or you could just deploy a single image, say a Singularity container image on your cluster, and then you can get started with a good collection of packages targeting both HPC and AI/ML. You can start with, say, a Singularity image. You could just download this, and you can you can download it for x86-64. You can even download it for PPC-64LE, and just use Singularity to get access to all of these 100 different packages. We have support for different GPUs from all 3 vendors in this full-featured image. And for x86-64, we have support for Intel GPUs, AMD GPUs, and NVIDIA. We have packages that support all 3 GPU runtimes, such as Cocos, which is used to express node-level parallelism using C++ Lambda functions and templates. And we have tools like Tau, which can support performance evaluation across all 3 GPU architectures. In case you're wondering, how does it look like if I download this Singularity image and say Singularity run? You can see all the packages that are installed here. They're the first 50 packages and see the locations. This is an Ubuntu 2004 image with runtimes including Intel 1 API. Yes, this includes the Intel compilers. It includes Intel MPI and the latest versions like 2022 or the AMD ROCm, including 452 or CUDA from NVIDIA. which has 11.4.2, or NVHPC from NVIDIA 22.1. And you can just say Spack find and a product like Spack find CUDA. You can see the CUDA installation. You can see DPC++ compiler for SYCL. You can see HIP-CC for HIP AMD. You can see the NVHPC compilers, which includes OpenMPI and PGI, what used to be PGI compilers before, but all installed using this. We even have other packages and languages. Now I know that Julia is a very popular and emerging language, and the more mature languages like Python are all there with AI products with GPU support. So you don't have to learn how to build TensorFlow or how to build PyTorch with GPU support. You can just deploy it. We have 3D visualization tools in the Singularity image. This includes ParaView, Visit, ParaProf. You can see all of these packages like ParaView, PDT, Tau, Tasmanian, Trilinos, HDF5, and other tools. There are 100 different packages on x86-64. There are packages for IBM Power 9. You can see over here, CUDA is supported, NVHPC 20.22.1 for IBM Power. And the Open Power community would be very interested in these 100 packages that are all installed. We have AI packages for NVIDIA GPUs. You could have a system with, say, an NVIDIA T4 GPU or the AC922 with a V100 GPU, which you can use with TensorFlow, PyTorch. Here are all the 100 different packages now available on the IBM Power 9 systems that you may have. So we have full-featured images for these two platforms. We have Docker and Singularity images. You can just say Docker pull with ECP E4S-GPU, and you will get the image which has support for GPUs. You'll be able to download the full-featured image for Singularity like this. We even have an LLVM DOE E4S image. And you can see over here, these are the PPC64LE images with 22.02 tag at Docker Hub, where we have 100 different E4S products. You can just say Docker pull, and you'll be able to get this for both IBM and x86 platforms. Here, we see the instructions for installing Spack and installing the E4S distribution based on Spack on bare metal platforms. Whether you're on IBM or x86, you can use these, and you can just cherry pick the packages that you want. You have a spack.yaml file, and in the directory in which this file is installed, when you clone this repo, the environments, you can then pick the MPI, you can pick the compilers, you can enable the different flags and variants. These are all the variants of solvers that we have in Trilinos, but there are many different packages, and we have a curated selection of these. So you can see the CUDA specs for PETC, for PAPI, MFEM. We have the ROCM specs, and they're built for different GPU options. Like this is for MI100 or MI250X GPU, the latest GPU from AMD, one that will form the basis for our frontier platforms. And you can build with one API as well. Now, if you're building a package, how do you speed it up? We have a build cache. This build cache has binaries. Binaries built for a number of different architectures, operating systems, compilers. We have created a collection of these binaries, and when you say Spack mirror add the E4S cache.e4s.io, then you can download this collection and just the packages that you need. We have over 80,000 binaries in this build cache now, and it's growing every day.
Customs instances are the novel eightfold path and SAT.
Excuse me. E4S base container images are available for x86-64, PPC64LE, and ARM64 as well. And there are all these different runtimes that you can target. You even have GitLab continuous integration CI images available for runners. And you can see over here that they have support for all these different architectures, including NVIDIA, for IBM, for x86 64 and ARM64 for base images. So you can create your own image using Spack. This is for AMD, ROCm. This is one API from Intel. And just the plain base image that we have been updating. The base images are very popular. As you can see, we've had over 1 million downloads now for the E4S image on Docker Hub. And these are the custom images and even links to how it is deployed at different facilities. We also have an AWS EC2 image, which you can use with this AMI. And it's a remarkable image which has a number of these tools. And you can see over here, it has AWS support for DCV. And there's a ParaView GUI. This is the Tau ParaProf visualizer, and you can run it. You can even run the E4S image within this. You can see a number of different tools that are all included in this image and the AMI. The doc portal has information about all the different packages. And you can search for different packages in different areas, and you can get information about this. This is the package description for Adios. These are the GitLab runner images for IBM Power 9, where you have on Docker Hub bare bones images, multi-platform images. And so with this, I would like to say that, E4S is a curated Spack-based distribution. It is not a closed system which only takes contributions from DOE, but it's extensible open architecture software ecosystem that accepts contributions from US and international teams. You can think of it as a framework for collaborative open source product integration. You can think of it as a full collection of software capabilities and a manifest of a la carte selectable software capabilities, a vehicle for delivering high quality reusable software. And I think of it as a conduit. I think of it as a conduit for future leading edge HPC software targeting the next generation scalable computing platforms and a hierarchical software framework to enhance software interoperability and quality expectations. I would like to thank the Exascale Computing Project for their sponsorship of the E4S project. And with this, let me take a few questions and show you some demos of how our Singularity container can be used. This is the Tau visualizer running all from the Singularity image. And you can go to the E4S web page, go to download, and just download a PPC64LE image and get started. Are there any questions in the chat window or someone who wants to raise their hand?
Let's continue, Sameer. At the end of the session, we'll have questions.
Sounds good. Let me just show you how I can take a single image. Okay, so here I say Singularity run --nv and ecp.simg. This is an image that I just downloaded from the E4S web page. The --nv gives me access to the NVIDIA GPU. This is on x86 64, and I can now use Spack to load the packages that I want, or I can even use other tools that are available. We have rich Spack. So I can say Spack find, and it will show me all these packages. I can say Spack find -dl, so dependency listing of a package like Trilinos. And it will show me how it has been built for different platforms, including a version called Trilinos at Develop, which uses MPH. And you can see the hashes which uniquely describe a particular instance. So you can see the dependency with packages such as CUDA over here in this. Now, these are the first 7 characters of a hash. So I could just say Spack find -dl -verbose, and even instead of trilinos, I could just say this hash, and it will show me how this package was built. So it says it was built using CUDA 11.4.2, and it's using CUDA architecture as 80. CUDA architecture 80, which represents the SM80 architecture, is for the A100 GPUs. I can say NVIDIA SMI, and it will show me that there are 2 A100 GPUs that are accessible from this. I have NVCC. I can say this is coming from the NVHPC 22.1 Spack find NVHPC, and it will show me the NVIDIA package. If I want to use Conda, I have mini Conda installed in my path, and I can say Conda activate ROCm for AMD GPUs or CUDA for NVIDIA GPUs. So with this, I can go to a demo directory. Here is the opt demo directory. I can go to Python tests and say I want to use Python packages. Here is a single NumPy example. And if I want to look at a PyTorch example. Now, if I had to install PyTorch from a scratch, it will take me a lot of effort to do that, to target the A100 GPU. And here is an example of using PyTorch. Here is another example using Keras with TensorFlow and using the GPU over here. Here is PyTorch using the CPU. You get the idea. Here is NumPy, again running on this. So I have a number of tests like this. PyTorch using GPU, and it shows you the name of the GPU. So these are 6 tests that I have put together that spans a broad range of these packages. I can say Python, I can say import TensorFlow, and then it will load the TensorFlow in the CUDA environment. So I can say TensorFlow /_ version, and it's using the latest 2.80 version of TensorFlow. I can say TensorFlow test is GPU available to see if it can access the GPU from here. And then it can show me that, yes, there are 2 GPUs, device 0, which is A100, device 1, which is A100. If I want to run all of these tests, let me say run.sh. It's running here. F1, F2, you can see the device name from PyTorch is A100 GPU. F3, it's using TensorFlow and running the test case. F4 is using PyTorch on the CPU, NumPy. You have OpenCV. You have a number of different packages in Python. Here is PyTorch using A100 GPU. And all I had to do was really download a single file from here, put it on my system, and suddenly I have support from 3 different GPU architectures. And I have support for AI ML packages like TensorFlow, PyTorch, targeting the different GPUs. Okay, I have MPI in my path. And also we can use modules in this singularity image. So I can see all the modules, and I can use the module load, unload. If I wanted to use visit, I can do that. Here is an example of using the same image. This is the singularity image. I can say paraview, and here I'm running this image all from within the singularity container. So here I can pick this. I can rotate this image. So graphics packages are all available. They work here. I can say module load Julia, for instance, and run Julia over here. And you can see that it's available here. Now, let me just show you real quick that I can also do this on an AMD GPU. So instead of --NV, I can say ROCm and then ECP.SIMG, sorry, Singularity run. And then I could activate the Conda environment for AMD GPUs with the same image over here. So in this case, I'm now going to here, Python tests, and I can run this. First of all, I need to say Conda activate the module for ROCm. Now I have ROCm in my path. Now the GPUs are all available. And I can see the ROCm SMI. I have two MI100 GPUs over here. I can also see Spack, find Trilinos, and you can see the packages that are installed here using Spack. You can say run.sh for the same set of tests. And you can see the F1, which used NumPy, F2, which is now using the device MI100 GPU from AMD. And then this is using TensorFlow, again with GPU 0 and 1, which are the NVIDIA AMD GPUs, the 32 GB MI100s. And you can see the ROCm Fusion is enabled, and it's using the TensorFlow. So this shows you that whether it's Intel or AMD or NVIDIA, all three GPUs are supported. I may have a window here on IBM systems. And again, I can say Singularity run --NV e4s.simg. And I'm then using the image on an IBM Power 9 system. And so this is what we had for PyTorch on AMD GPUs, PyTorch on CPUs, Singularity. And now here, this is an open power system, an IC922 with NVIDIA GPUs. And if I say NVIDIA SMI, you can see it's running CUDA 11.4, and it has Tesla T4. And let me just try doing the same thing here. Python tests, Conda activate CUDA, and I can say run.sh, and then I'm running in NumPy on the IBM Power 9. The same set of examples. This is PyTorch detecting the Tesla T4. So I didn't have to do anything special. I just download a single image. I just run it with Singularity or Docker, and then I have pre-compiled binaries all set up for me in an environment that supports modules, which supports Spack, and I can use GPUs on different architectures. Here is another system where I can go to images, Singularity, run, and here I can use the Intel GPU, which is now accessible through E4S. I can say source opt Intel 1 API that vars.sh, and then I will have access to all the MPI, DPC, PP, MPI, ICPC, Intel compilers, which ICPC, which iFort. I can say CLinfo-L and see that I can access the XEmax graphics GPU. So if I had samples, GPU, samples, DPC, gem. If I had a DPC++ program like this, it's a sickle program, and I want to compile it with DPC++, access the GPU, I can do that. Let me just build it. I can say module load CMake. I can get CMake all from Spack. And I could have also said Spack find CMake, and then I can see the different package versions that it has. And I can just go to the build directory, say CMake ... It's using DPC++, GCC, and these compilers. I can say make. And here is the DPC gem. I can say GPU 4000. So it will take 4000 by 4000 matrix. It will run it on the Iris Xe Max graphics card like this. If I have a tau, I can say tau exec serial level 0 with level 0 and event-based sampling, and enable this. And you get the idea. With this, I can now access the performance data from tau. I can see the execution of a kernel called gem, which took 6.9 seconds over 4 calls, and see the level 0 API. I can also run it in paraprof like that. So I'm able to access GPUs for Intel, AMD, NVIDIA, use AI ML packages. I can use the GUI tools. I can use IBM Power 9 with NumPy, PyTorch, and here is the execution on the GPU. Here is the function that's taking 6.9 seconds on that GPU. The gem call for the DPC gem application for DPC++. So one API, NVHPC, and ROCm are all there. You can learn more about Spack and see how it supports CPUs and GPU executables on IBM Power 9 systems with all of these packages. Now you can see there were 500 packages that were installed with many Python packages, many packages like Raja or packages like MFEM or SuperLU and Tau and Trilinos, all installed using Spack. So with this, I'll stop over here and see if there are any questions for me.
Team, thanks, Sameer, for the presentation as well as the demo. Participants, any questions for Sameer?